it soon. So I've been using this to coach some projects through the overall structure of the document, looking at the current deliverable for you folks. Your deliverables seem fine on most of this, but knowing we got a lot of people in class who may be watching this workshop in a recording, let me just run very quickly through this. And this is material that I posted in the Unit 13 question and tips thread the other day. So thinking back to the way your project has worked, everything starts back there with stakeholder requirements. And it takes practice, but if there's a common error that a lot of engineers make when they're writing requirements, is that a lot of the requirement statements people have been writing actually describe some of the functionality of the system that you're going to design. And that's technically incorrect. The requirement statement should just be a requirement statement. Okay? But letting a requirement statement describe function is better than having it describe technology and components. So if you're going to have a requirement statement that goes a little too far, at least going to the function level isn't so bad. Here's an example of a requirement statement that, because I haven't told you the kind of system we're talking about, it actually tells you almost nothing about what's going to happen in order to meet this requirement. You would have to have project context for this to make sense. And I did that intentionally, just to get a requirement statement that is reasonably correct, but doesn't mean much outside the context of a real project. So in terms of how to do this requirement, we're going to capture the customer's needs and allow them to change their minds. Is the basic requirement. So in this particular example, I translated that into a stock and flow analysis that said, we're going to have customer orders. Customer order is my internalization of what the customer wants and what they need. Because orders really only exist within our systems. There are no orders out in the real world. Orders are what we create in systems because customers want things. So I want my system to manage a stock of customer orders. So I'm going to have new orders coming in and canceled orders coming out. Maybe a lot more complexity to that by the time I'm done. But for now, I can just say on a very simplified basis that I can use this stock and flow. Try to get some better light in here. I can use that stock and flow to represent that requirement. So this stock and flow would map back to that. So if this is the stock and flow, and a lot of people have been doing stock and flow, but some are definitely better than others. So notice this is a stock of orders. So the only thing flowing in are orders. The only thing flowing out are orders. That basic rule for how to manage a stock gets broken by a lot of people in their projects. Again, perfection is not expected in this class, but generally it takes, after a few projects, you'll find you're getting more and more comfortable with the idea of stock and flow. In fact, I recommend after you take a few more classes or work for a year, go back and read the Meadows text again. It can be insightful to read that text again after you've developed some stock and flow diagrams for a while. So this is the stock and flow that would meet that requirement. So the next step would be our functional architecture. How do we develop a functional architecture that will implement at least this portion of our system? And that's a fairly mechanical process. I think people struggle with it partly because they don't accept the fact that it's almost a purely mechanical process. So every arrow of a stock and flow is a function. The stock is typically one or more functions because something has to happen while it's in there. So I've got to be able to take orders, I got to be able to store my orders, and I've got to be able to cancel my orders. Just looking at the stock and flow, I know I'm going to need that. So I could draw my decomp for this particular one. Now, the functional decomp for the entire system might be a huge diagram. This is just a little tiny slice based only on that particular stock and flow. So I need a function for managing this stock, okay? And within it, I need a sub-function for entering the orders that are arriving, a function for canceling the orders that I'm taking out, and some way to store the orders in between. So stock and flow implied this diagram. Okay, so often when you're doing functional architecture, it pays to let the diagrams do more of the work. There's a lot of people in this class that are busy working too hard. If you're trying to come up with this stuff yourself out of nowhere, it's really, really hard because there's a million ways you could describe the functionality of your system. So the easiest way to do it is let the diagrams do the work. Take the stock and flows that you've drawn and just arbitrarily create the functions necessary to implement them. And then you've got a bunch of bricks. Now you can arrange into a wall. So yes, you still have to build a wall. So the ultimate question on functional architecture is, what are your major functions? Okay. To know what your major functions are, you've got to keep in mind your mission and your basic high-level requirements. Don't say all the requirements at one time in your mind. You've got to remember what your system is about. Because the rule of thumb on defining any kind of decomp is whatever your system is, you should be able to define it in roughly 7 major functions, plus and minus. A real simple system might only have 5. Okay, a really complex system might have 10. But that's kind of the range of what a functional decomp is going to end up being. If you have a lot more functions than that, chances are some of them can be grouped and put into a different branch of higher order functions. So for me to know what my manage order functions fits into my architecture, I have to know something about all the functions of my system. Okay, now remember, functions of your system are verbs. Okay. In the 52 class, the architecture class, we learned to use verb, noun, constructs. With everything that's functional has to be the verb that is the function operating on an operand, which is a noun. So the easiest way to name a function is to use a verb and a noun construct. And because you don't design functions to be used only once, usually, almost always, the noun should typically be plural. Okay, so my function is manage order. Manage is my verb and orders is my plural. It's not manage order. I might eventually in my technical architecture have a procedure for handling one of them that would be called manage order. But in terms of a functional decomposition of your system, your functions should really be dealing with plural operands. So in this particular example, I don't know where manage orders function fits into my system. I don't know how big my system is. So maybe managing orders is a major subfunction. I don't know, because I didn't provide any context for this project. It could be that it's a low order function within one branch of the major functions going on. I had a meeting with a student today who's designing a light rail system. And when he listed all his functions for his light rail system in his city, he had about 50 functions. So we spent some time on the phone today just talking about that system, saying basically, you can't have a system that does 50 things. Yes, the system can do 50 things, but you can't draw a decomp where there are 50 major functions under the root of your diagram. It's not manageable. It's not that it's syntactically impossible. It's just that nobody would ever design a system to be used this way. I like to urge people, when you're thinking about your major functions, think about having a functional manual, a user's guide for your system. Okay, your major functions are the chapters. Okay, so what are the chapters of your functional overview of the system? A description of your system is going to list out major functions. Now, for this light rail system, one of the major functions the student wanted to have was the sensing system that controls access to track blocks. So when a train enters a block of track, the sensing system turns on the red light at the end to make sure no other train will enter the block while this train is in it. And at the other end, when the train leaves the block, moves on to the next block, the sensing system will turn the entry light to green. So that's an important function, very, very important function in the system. But the student tried to make the sensing and signaling system one of the major systems overall in the system. And the mission of the system was to provide public transportation to citizens in the city that was easy and effective and available, blah, blah, blah. Okay, so something along that line in the mission. And we discussed it for a while, but I eventually got the student to see that while signaling and control, while signaling is important, nobody builds the system in order to do signaling. Okay, that's not what the system's about. So signaling is very unlikely to be a major component of the system. So this is a case where the student was basically thinking too much like a mechanical engineer. He wanted to make the components of his system, the trains, the tracks, the signals, things like that, which would be fine if this were a mechanical engineering class, but it's not. It's a systems engineering class in an industrial engineering program. So the system has to be a societal system. So we went back to his mission statement, providing that effective, available, inexpensive public transportation. I said, what does the system have to do to provide that? What does it do? Not what is it made of, or what does it have? So we're not talking about trains and tracks and signals, but what does the system have to do to fulfill its mission? That's the question you should all be asking yourselves as you start to finalize your document. Really look back at the functional architecture and say, can I answer the question for my mission? What's the system have to do to make that a reality? Can I answer that question with roughly 7 major functions, plus or minus? In the case of the light rail, they have to, maintain and inspect their track. They have to plan and schedule the trains. They have to outfit and operate the trains. They have to operate and provide services at the stations. They have to maintain their rolling stock through maintenance. So we ended up rattling off 5 or 7 major functions of the system. And one of those major functions is you've got to control the network to deliver safety. So controlling the system, controlling what's happening in the system, that is a major function, because the mission included safety. So we eventually saw that there were major functions in the system, but none of them were sensing. Okay, the sensors come down under some of those other functions. So eventually what we saw was that the controlling function would eventually need a function to sense when a train entered a block, and it had to have a function for closing the block to traffic. That's going to be the red light in the design, but there's no red lights in function. We sense that a train has entered the block. That's a subfunction, low-level subfunction, and we have a subfunction for closing the block. Okay, that's what's going to happen. Over in the technical architecture, that closing the block might get implemented as a red light. Okay, but all by itself, that is about control and the control function, but it doesn't really work until over in the operate the trains function, an engineer who's operating a train sees that closed block and stops the train. So sensing and controlling are functional aspects that have to integrate things across functions. And that's what we eventually had a discussion about, and why sensing in our light rail is so important, because the sensing system says this block is occupied, therefore it's closed. The sensing system can't stop a train. It just says this block is occupied, the block is closed. Over under operations, the engineer in those procedures spots the closed block and stops the train, doesn't enter the train until clearance has been provided. So again, the sensing system eventually senses that the block is now clear, train has moved on to the next block, and therefore the sensing system opens the block again. And it's only when that green light appears that over in the operation subfunction, the engineer gets that green light and resumes travel for the train. So the functions to do what this person wanted to talk about were actually scattered all over the system, but they made sense when grouped under the right major functions. Okay, there's no magic to coming up with the right major functions. I can't give you a formula that will do it. The closest I've ever been able to come to the formula is to say, basically, you want 7 plus and minus. Because most of us as engineers, we're pretty good at coming up with functions of the system. So the problem isn't that we can't think of functions. Usually the problem is that we think of too many, and we go down too low a level of detail, and we mix up our levels of detail. So review your functional architectures in your document and ask yourself, how many major functions do I have? If I were to write a guide to my system, what would be the chapters? And that's what your major functions are. In terms of that light rail system, it was planning and scheduling routes. It was assembling and dispatching trains. It was maintaining the trains. It was operating the actual commuter lines. It was servicing customers at the stations. There were about 7 major things the system had to do. And you'll know you have the right list when a reasonable person could look at your list, compare it to the mission, and say collectively, those functions will fulfill the mission. That's the quality control check on all of this. Okay, can it fulfill the mission? So often people have a list of major functions, and it looks right, it sounds right, but someone looking at it and comparing it to the mission might have that gut feeling that there seems like there's aspects to the mission that these functions wouldn't fulfill. So that's what you're doing. Like I said, I can't teach you magic for that. That's the hard part of this class, is that there's no magic formula for knowing you have the right functions. But that's why this example is important to me, because to the extent you're working hard on your project, I want it to be you figuring out what your system needs to be engineered to be able to do. I want you concentrating on your actual system, not on the diagrams and tools that we're generating. Getting from a stock and flow to a functional decomp is a mechanical exercise. You should be able to do it mechanically without giving it a lot of thought. Don't waste your brain power doing the stuff that the tools do automatically for you. So get faster and more mindless, if you will, at doing the automatic stuff so you can actually devote your time to the engineering. And that's the interesting stuff we all got into this for. Okay, and usually that constraint of 7 major functions, plus and minus, that constraint is usually good enough to get you to a pretty good design. Because if you put together all your functions, you've got 15 major functions, you know you're not done. So you look at that list and you stare at it and say, which of these can be grouped together? So I can invent a new major function and cluster 2 or 3 of these under it. Okay, and now I have a shorter list. And you know you're done when you're down to that 7 plus and minus, and you don't have a tendency to want to merge and combine them anymore. You also look at the major functions. Are they all major in kind of the same way? Are they all really big hunkers of functions? So you don't want to have 5 major functions, some little pediddly thing stuck off to the side. They're just kind of an add-on. But your major functions should be the major functions. So somewhere under this tree that I'm showing you here, manage orders functions would connect to the diagram. And depending upon the scope of the system, maybe managing orders is a major function of the system. I haven't given you enough information to know. That's really doing the functional architecture. Then you move on to technical architecture. And it's going to be a mechanical process. So let's take a look at this managing order function. I have to be able to enter orders, I have to be able to store orders, and I have to be able to cancel orders. So there's 3 things going on. Okay, now again, I'm making a leap here in terms of what might be the design of this particular example, but let's assume that I'm using a reasonable amount of automation, that I'm going to store orders in a database. So I just need transactions to enter orders into the database and update them when I cancel them. So I'm going to assume a fairly traditional order function here as I move forward. But if I make that presumption, if that's where I think my architecture is going, it's pretty easy to get from this functional diagram to this system diagram. So again, you're looking for ways to do what we're learning in this class without having to waste a lot of brain power. So this is a mindless adaptation, but it does include a leap here that the basic underlying technologies I'm interested in, using a database to store orders, is sound for the project. If that assumption isn't true, then maybe some other path would go. And that's why you need to know roughly where your project's going when you're working on your architecture. But if you don't know where your project is going in terms of the types of technologies that are available to you, you probably shouldn't be developing a technical architecture yet. So basically, at this point in your project, you should know these kinds of things. In a real world project, you always will. In fact, one of our problems as systems engineers is we tend to think of these technologies way too early. I've seen high-level requirement statements from stakeholders that are already talking about databases. And there's no such thing as a stakeholder requirement for a database. So the danger isn't that you'll get here and not know what technologies to talk about. The danger is you'll already know the technologies and you will have allowed them to corrupt the functional architecture and the stakeholder requirements. This technical architecture should be the very first place you start to talk about things like databases. If you've talked about databases prior to this page, you're out of sync with the methodology, with the engineering. So I have a function back in the functional architecture. This is I have to be able to store orders. So here in the technical architecture, I'm going to include an order database within which I'm going to do that. And the functional architecture had 2 types of other sub-functions I have to be able to do for those orders: enter orders and cancel orders. So those are functions. What I have to do is enter orders and cancel orders. How I'm going to do it is the job of the technical architecture. So I'm going to need some kind of an order entry transaction to get the data into the database. And I'm going to need a person, an agent, to execute that transaction to put the information in the database. So anytime you've got a function that requires doing something like this, make sure your technical architecture includes the target of the transaction itself, and the person that's going to do the task. That's the difference between a societal system and a mechanistic system. Societal systems are about how people are interacting to do things. So an order agent is going to execute an order entry transaction to put an order in this database. Okay, we also need a transaction for order cancellation, and order cancellation, a person who will execute the order cancellation transaction to update and cancel orders in the order database. I put all this together and I call it an order management application. So now I'm talking about an app, probably a piece of software, a set of procedures for implementing this function. It didn't have to be those technologies. It could have been a completely different technical architecture. But technical architecture is where we start to commit ourselves to how we're going to do something. If the intent had been to record orders on a flip chart, I'd have a very different technical architecture. This functional architecture would be the same. So I could have designed a technical architecture that records orders on a whiteboard out in the plant. I could have done it in a spreadsheet. I could have done it on a cork board someplace. I could have done it with Post-it notes that I stick on the wall. Whatever technology you decide, that's your job as an engineer. But the technical architecture is that representation of that which you choose to do. Now so we're talking this week about trade spaces in the other class. You might need at times to develop a technical architecture with lots of variations in it. Okay, I could have polymorphic variants of this order database. I could implement this database in Excel. I could implement it in SQL. I could go out and buy a commercial off-the-shelf software package. I could implement it as a flip chart or a wall chart or a whiteboard on the wall. So I could, in my architecture, explore polymorphic variants of this component. And I could list those down here as the children of that component. So you're committing to the technologies you're reasonably expecting to use. So if you're unable to make a very firm commitment, you'll tend to document your technical architecture with more and more options in it as things go through. Now, this is not the technical architecture I would implement for that function. This function implies two transactions and some kind of data storage. Transactions, subfunctions that are transactional have to have people that do them. So I've got two transactions, people to do them, and a place to put the results. So this is what I get when I mechanically translate the functional architecture into a technical architecture. But I don't stop here. I look at this diagram and say, does this really make sense? Is this how I want to engineer my system? And it's not. The reality is I don't need an order entry agent to be a separate component of my system from the order cancellation agent. I should be able to have an order agent that can do either of these things. Why would I create completely independent roles in the system and staff them that way? So while it made sense to translate what I had, this isn't where I'm going to stop. It's really where I'm going to start. So you start by translating things into this kind of mode, and then you improve your engineering. So as long as I'm making improvements in this diagram that are technically better architectures, without changing how this work maps back to the functions, then I'm going to be fine. So this diagram will meet the functional requirements, but I want to make it better. So I usually start by looking at the people in the system. If I've got all kinds of transactions being done that are reasonably close together in complexity and scope, I don't want separate agents doing them as I go through. So I'm going to modify the technical architecture to look more like this. Let's take the two agents and merge them into one agent. So I still have the database, I still have two transactions, but now I have an order management agent. I inherit the name from up above because the agent is no longer defined as transaction specific. So now I have an order management agent within the order management app who's going to execute two different kinds of transactions against the order database. Okay, so this is still a valid technical architecture as long as it makes sense to merge those two agent roles from this diagram. If it doesn't make sense, then this diagram won't make sense. So the fact that I'm drawing it doesn't make it true. That's what verification and validation is all about. So maybe I'd want to verify with someone, does it make sense to treat these two agents as one person can do either? Well, maybe it's not. Maybe the scope And the role of the system is that the order entry agent needs a lot of extra training because their job is to upsell the customer, to cross-sell, get them to buy more. Any clerk can cancel an order, but these people are expected to do a lot of upselling. I'm going to invest a lot in them. So because I'm going to make a major investment in my order entry people, I don't want to waste their time doing cancellations. So maybe if that's the case, I'd want to keep these two roles separate. I would not be able to verify or validate with my stakeholders that this combination I put together makes sense. Remember, it's their system, not yours. So you're trying to engineer a better system. You're constantly needing to verify and validate all these changes that you make. So this diagram is only valid if my stakeholders would agree the same people taking orders could easily handle canceling them. Let's assume that's the case now. Okay, so I'm constantly looking for those kinds of ways to modify my technical architecture. So let's do another one now to say, chances are my order management agent isn't just managing the orders themselves. Okay, because order management is going to be part of a broader functions. This goes back to what were the major functions. So let's assume order management was not a major function, that it turned out order management fell under a major function called maybe customer service or serve customers. If that's the case and order management isn't kind of the end all, then instead of treating it as an order management agent, I can modify the architecture again to say, really, this is going to be part of the customer service subsystem. Order management app is part of the customer service subsystem. And at the level of the subsystem, I'm going to design a role for the customer service agent that could easily take orders and cancel orders, as well as a host of other things that might be needed within this subsystem. Again, we're only looking at the portion that I derive from that one stock and flow. So again, I'd want to verify and validate that. But I'm basically going to my stakeholder and saying, instead of teaching someone just to handle the transactions within my order management, I'm going to broaden that person's responsibility so that they can act as a customer service agent. They will take orders, they will cancel orders, but within the context of customer service, there might be dozens of other things these people could do. So I'm inventing that new role. I'm also recognizing here that maybe I wouldn't want to build a database just for orders, that I have a customer service database that has marketing stuff and price lists and all kinds of things related to my customer profiles. And I'm going to put orders in that database. But I'm not going to build a separate order database. I'm going to put order tables that meet this functional requirement. I'm going to build that into the customer service database. So again, whether that makes sense or not requires me to know stuff that's off the page, is what other functions were needed within my customer service function that might be supported by this. So customer profiling, pricing, contracting, accounts receivable, any number of things might also be needed within my customer service subsystem that would cause this diagram to make more sense. So again, I've been modifying my technical architecture since I got here from the functional architecture. This is the one that starts to make sense as I go through. And again, you ultimately have to decide how this fits into the subsystems of your overall system. So just like your functional architecture was based on 7 plus and minus major functions, most systems we design will have 7 plus and minus major subsystems. The simpler systems have fewer, the complex systems might have a few more, but nobody engineers a system to have 100 subsystems. The logic of the semantics of the term subsystem doesn't make sense. So at some point you're trying to figure out, just like you did back in the functional architecture, how can I describe my system with 7 plus and minus subsystems such that I am in fact describing everything the system has to be able to do to meet everything the system has to be able to do in the functional architecture. Okay. And that's what this diagram is about, as I see more with you. So in this case, I'm declaring that the customer service subsystem is broad and big enough that I end up treating it as a subsystem. Back in the functional architecture, I never resolved that here in the example. So sometimes I'm just going back to the functions. I'm inventing functions from the stock and flow. I'm going to invent the major functions based on my knowledge, and eventually they meet up. So eventually, in my functional architecture, this manage orders function has to connect to a major function someplace if it isn't a major function itself. So eventually they need to be connected. But I might do that in a top-down fashion by inventing these diagrams. On the technical side, I took more of a bottom-up approach. I do the design of the functional architecture to get the default architecture, and then I improve it by aggregating things. I aggregate the role, I aggregate this piece of the system into a broader subsystem, and eventually I find that I've aggregated enough that it makes sense to use that subsystem as one of my major subsystems. And that's basically how all this works as I see my way through. So that's the example I posted in the discussion the other day. I just wanted to share it with you and to share it via the video so everybody in the class can see it. But that's the thought process you're going through in your class. The decomposition diagrams are the easiest diagrams to draw and the hardest to get right, precisely because there's an element of these decomps that's mechanical. You just kind of plug stuff in. But there's also an element that is the most creative aspect of your engineering, and that's figuring out what all these branches are, and actually naming the subsystem, naming the functions. The most common error I see in both functional diagrams and technical architectures is people have a tendency to not name the function, but to name a category of functions. Okay, so for instance, back in that light rail system, trains are not a function of the system. They're a component of the architecture, but they're basically the rolling stock. They're not, there's no trains function. There's no human resource, well, unless you're writing a human resource system, there's no human resource branch. So I saw one project the other day that all the people in the system were in the technical architecture like they're supposed to be, but they were all grouped under a single subsystem called people. And I had to challenge the student and say, how is people a subsystem of your system in a major way? Well, that's where all the people are. I said, no, it's a societal system. People should be scattered throughout your system. You'll know you're doing it right. When you're dealing with a societal system like this, you should see procedures everywhere. If I drill down one more level, I'd have a procedure for doing the order entry transaction. I'd have a procedure for canceling an order. So if I drill down farther, procedures start to show up under these things. And in a societal system where people are doing things, most of the low-level activity is going to be procedures. What's the procedure for entering an order? What's the procedure for canceling an order? In the railroad side, what's the procedure for stopping a train? What's the procedure for passengers to board a train? What's the procedure for pulling into a station? What's the procedure for taking a train offline for maintenance? What's the procedure for closing a track because of an accident? Most of the, if you've got a complete technical architecture, most of the bubbles are procedures. That's how you implement systems. You have procedures for doing that, even if the procedure is completely automated, like a procedure for sensing that a rail block is occupied. Doesn't involve any people. There's sensors built into the line, but at some point, someone had to write the procedure for how the control system is going to detect the train in the block and how it's going to signal the closure of the block. So even if there's no people involved, we still implement systems through procedures. Those procedures have to be documented. So the majority of your technical architecture should be the procedures that are being executed by the people in the system. Now, I say the majority is procedures because back when I started, I could have said you're going to be half procedures and half agents, job descriptions. But because my bias is that I don't want 1,000 different job descriptions in my system because we don't build real systems that way. So I end up writing oops, I'm going the wrong way. So eventually I need the job description for the customer service agent. So I might have their position description under this box as I decompose it further. The component is the service agent, but the components of the service agent are their job description, might be some of their orientation materials. It might be some of the standards they have to work to. So what do I have to tell this agent in order to do their jobs? So the customer service agent is a component of the system. So what is that component? It's their job description and their training for the most part, but also potentially some tools they might have. So if they have personal tools that they use, I want to list them under the agent. Okay. So every customer service agent has a train schedule app that they carry around with them. Every customer service agent has, I don't know what. I've never run a railroad, so I don't know. But that's what this would think of. So the majority of your boxes should be procedures. A lot of your boxes should be these agent roles, such that I can look at your technical architecture and see who's doing all these procedures. And then you happen to have the actual infrastructure. In this case, it's an IT thing, it's a database. But it might have been storage bins in a warehouse. It might be the vehicle they have to drive if they're going to go out and do site inspections. So there's all kinds of equipment and stuff that's be part of this as well. But because we're dealing with societal systems, a lot of your system is the and the procedures as you're working your way through your design. But notice you end up with a very distinct set of things. So for instance, if I'm looking at the functional architecture, every box in a functional decomposition is a function. We call the lower ones subfunctions, maybe sub-subfunctions, micro-functions, whatever you want to call them. So there's a difference between a micro-function and a major function, but everything in this tree is a function. So you ought to be able to name them with verbs and nouns. What is the system going to do? That's what the functional model is for. So everything is a function. When we get down to the technical architecture, we tend to name the components of our technical architecture differently based on what it is. So typically I refer to them all as components. They're all components of the system. Some of them are subsystems, the big honker subsystems. Some of them are apps. Some of them are databases. Some of them are people, agents. Some of them are procedures. Some of them are tools. Some of them are modules. Some of them are assemblies. Some of them are reports. Some of them are checklists. Some of them, whatever they are, there's a million things that might become a component of your system. So where the functional architecture is nice and clean, every box is a function. You don't have that here. Because to get from the functional architecture to the technical architecture, you had to overlay on that your sense of how you are actually going to implement the system. So if the system's completely manual, you have a lot of procedures and forms and checklists. If the procedure is primarily an IT system, you're going to have a lot of databases and apps and things like that with transactions. So to get from function to system, you have to decide what kind of system are you designing. So within your technical architecture, that stuff becomes relevant. But it's not relevant prior to that. At no point when you're doing your functional architecture should you be talking about transactions or tables or databases or reports or anything like that. There's never a set of functional requirements for system components. The system architecture, the technical architecture right here is how you're going to meet the needs of the functional architecture. The functional architecture is what the system has to do to meet the stakeholder requirements and the mission. Very, very different purposes. So what makes this process difficult, more difficult, I should say, is the difficulty of not corrupting these various stages. If you look at your functional architecture, almost everybody that does this, particularly when you're doing it early in your career, everybody puts some system architecture into their functional architecture. It's really hard to get people to describe the functions of a traffic intersection without mentioning red lights, green lights, or stop signs. It's really hard to do because we're just so used to thinking of those as the functional components of the intersection that we don't know how to talk about the intersection without mentioning them. So it's okay to mention them as long as you're careful how you do it. So it'd be better to say you provide clearance to the intersection. That's the function. And eventually that gets implemented with a green light. You deny clearance to the intersection. That's the function. Eventually it gets implemented with a stop sign or a red light. But if you end up talking about stop signs and red lights in your functional architecture and you don't do a whole lot of it, that's okay. The criteria for doing well in this class, in my grading guideline, is that the architectures you put together have to be adequate to the task. That's a relatively low bar. You can make a lot of mistakes in these architectures and still do pretty well in this class, because this is just the systems engineering class. So the fact that you come out of this class knowing that you do your function in preliminary design, you do a functional architecture followed by a system architecture, and then you move into your detailed design. So if your process flow and your deliverable looks like that, you're going to do fine on the project. Okay, it has to be adequate to the task, is what it says in my grading book. Okay, now some of you will go on to ESI 6552, which is the systems architecture class. Some of you will, some of you won't. I don't know. You're all welcome to. That class is about taking what would have been an adequate architecture and turning it into a complete and optimized architecture. So that whole class presumes you've finished this class, that you're able to put together these architectural steps, but they may be seriously flawed. So we spend that class talking about how to get them right. What does a good architecture look like? So we raise the bar. So the architecture you produce in that class has to be a lot better than the architecture you have to produce here. Okay, so I'm okay with everyone in this class making these kinds of mistakes. To this day, when I design systems, I guarantee you, I stick some system function into my system component into my functional description, or I mention a function back in my stakeholder requirements. There's no requirements in the train system to have open and closed blocks, but it's hard to not talk about that. Instead, I should just talk about I need safety. Okay, the system has to be safe, has to avoid collisions. That's the requirement. The idea of there being blocks of track that are open or closed and engineers who pay attention to red and green lights, that's just what the system has to do and how it has to do it to meet the requirement of a safe system where trains don't collide. But the requirement is for safety. Okay, but I guarantee you, someone writing requirements for their light rail system are going to talk about open and closed blocks back in the stakeholder requirements. It always happens. So don't shy away from that. It's okay, but always look at what you've done and reflect on that. Look at your stakeholder requirements. Say, am I naming the function here? Am I naming something that really ought to be moved forward to the functional architecture? If you are, then move it to the functional architecture if you can, and replace it with a statement where you say to yourself, why did I name that function? Why did I name opening and closing blocks in a stakeholder requirement? Oh, because that's how I make the system safe. So the requirement is safety. Let's move the function to the functional architecture and replace it with a requirement for safety. And that's how you get more and more of these right. If every time you see a system component in a functional list, you move it to the technical architecture and replace it with what it does instead of how it does it, you'll be improving your architectures. So in ESI 6552, we do a lot of that. We say, let's get all of the functions out of our requirements. Let's get all of the system components out of our functions and really purify and clean this thing up as we go. And it's only once you've cleaned up your architectures in ESI 6552, you can then move on to the integration and testing class, ESI 6511. That class writes test scripts for all the different components, but it has to presume you've got a cleaner architecture than what you get in this class. That's why you're writing up your test stuff in this assignment, kind of loosey-goosey, I used to call it. Your architectures aren't actually pure enough to do a really detailed set of test conditions and scripts. It would be hard to write test cases, test conditions, test scripts, test data, test processes. It would be difficult to write the formal deliverables of the testing class against the projects you've done in this class, because too much of your architecture is still impure. That's why the 3-core series goes the way it is. So we take this class just to learn to develop an architecture. We use the next class to develop the architecture, and the final class develops the validation scripts against that architecture. So you're all right where you need to be in terms of progressing as system engineers, but there are a lot more steps to take even after this class. So I just wanted to share that example with you. It's in the discussions, but in the discussion, I didn't type up everything I just said. So I wanted to have an opportunity to offer it as a mini lesson. Any questions or comments on that? You all still there? Did I lose you? Okay, I'll stop that share then. So if we can, let's try to move over to some of you talking about your projects, either using what I just said as your framework or any other questions you want to talk about in terms of your projects. Any takers?
Oh, I'll open the floor because that's actually one thing that I noticed now after this discussion that I probably didn't include enough of were an adequate I would say, number of procedures, or maybe I have, and I just haven't viewed them that way as I've been writing them. And then a myriad of operator descriptions that I've generically captured as kind of one singular type. Even though I have a lot of the tasks explained explicitly, I may not have included the actual personnel job description in the particular architecture. So that's one thing I realize now that I made a note of, that I have to go back through, because I have their job functionality, what they need to be doing, but I've failed to include many of their roles in the actual technical architecture. So
it takes getting used to. The fact that you can even say that, that's very positive, because it's a real challenge in taking this class. And for me, it's a challenge in teaching it even, is that on the job, if I were to go out and look at system engineers on the job, some of our bigger industrial companies around the Central Florida area, I see a lot of projects where the majority of their architecture is the hardware devices, the mechanistic side of the project. The stuff that we remember, when as system engineers, we're laying out a general system architecture. We're not building the system. From what we're doing in this class, the next step wouldn't be build the system. The next step is really allocate all the requirements of your architecture to the appropriate engineering discipline. So eventually, my IT guys have got to get involved in designing and building all the IT components that I put in my technical architecture. So eventually there will be a software engineering project that gets allocated 10, 20, 30% of my system gets allocated to them. I may have hardware. I may have hardware and controls that have to be developed, and I'm going to create a team of mechanical engineers and electrical engineers who will work together to develop the sensoring and control systems that I've hinted at in my technical architecture. I don't know how to do all that work. Okay, so I'm not a software engineer, I'm not an electrical engineer, I'm not a mechanical engineer. So there's a whole bunch of stuff I'm putting in my architecture that for it to really work, I've got to allocate stuff to other disciplines. Likewise, there's going to be a host of requirements and components throughout your design that, for lack of a better term, I'd say they get allocated to HR. Say, hey, I need all these jobs defined. Maybe they're new jobs, maybe they're updated requirements for existing positions, but they're the ones that know, hey, if you add these responsibilities to this existing job, that would bump them up a level in pay grade based on their responsibilities. And we're not willing to do that. So they're going to push back and make me design it a different way, where they are willing to do it. It says, well, this new system, not only does it alter people's jobs and maybe create some new jobs, but it really alters the way we should be orienting employees when we hire them. So HR deals with all of that. I don't know anything about HR. So a whole bunch of my requirements and components should get pushed out to HR. So the real question that ends my project as a system engineer is, have I allocated all of my requirements to someone? Okay, and now not all requirements will get allocated out, because some of them get allocated to the systems engineer, and that's me. So I get to keep a certain amount of stuff on verification, validation, integration. The actual integration and validation of the system stays with me. But I'm going to spin off all these other smaller projects to the engineering discipline. I have mechanicals doing this. I have aeronautical engineers designing trajectory planning for my missiles. I've got HR people designing job descriptions and training programs and orientation. I've got IT people developing the IT components of my system, and that piece of most systems has gotten bigger and bigger over the decades. But most of the stuff I put in my technical architecture, I'm not going to personally implement. I'm going to allocate it out to the other disciplines. So you don't have to have it perfect. Your job as a system engineer, when you invoke one of those disciplines, is what you don't want is them to come back to you later and say, you asked us to build you a customer service database that includes some order tables. But the way you've described it doesn't make any sense, or the way you've defined it, you've put so much detail into your architecture, you've overly constrained us, and you shouldn't have done that. So at the very least, let's come back and talk about altering your architecture to include some polymorphic variants. The example I use in my MIS class for that is the ATM. If I say the way you authenticate a customer in an ATM is they put in a card and type in their PIN, if I make that a requirement in my technical architecture, then eventually someone's going to, a control person on the mechanical side or the electrical side is going to come back and say, you know, that's not the best way to do this anymore. If you hadn't locked us into that as your design, we might have done it with facial recognition. We might have done it with retinal scans. We might have done it with fingerprints. There's a lot of better ways to do this than having your customer put a card in and enter a PIN. But we'll have to do it that way if that's the way you leave it in your requirements. So are you willing to back off your requirements a little and give us a little more freedom? So that's the defect you're trying to avoid as a system engineer, is committing some other discipline of engineering to do it the way you think it needs to be done, when in fact they're the experts in their field. So my functional model for an ATM includes authenticating the customer, and I probably have a module in my technical architecture for authenticating the customer. And in my notes for that, I can either make it one module and write a lot of stuff in that module description, including in the old days, we did this with cards and pins, but this doesn't necessarily have to be done that way if there's a better way to do it. So I might just write that on that component. If I want to get really fancy, I might say this module has a number of polymorphic variants. One is the old-fashioned card and pin. Another is retinal scanning. Another is facial recognition. Another, you know, so I can define those options to say, based on my research and meeting with some of the engineers, we were actually defining an architecture that could go a variety of different ways. So my job as a system engineer is to not screw things up for the better engineers than me. Don't try to tell software people how to do software. Don't try to tell mechanical engineers how to do mechanical engineering. So the most likely defect I'm going to introduce in my technical architecture is I'll actually go too far, and I'll design in things I think are great ideas, but they're actually constraints that may not be state of practice today. I'm most likely to make that mistake on databases because I used to be a software engineer specializing in databases. So I'm probably more likely to think I know best there. But the reality is I haven't built a database in years. I assume databases have improved a lot in recent years. So I should not be constraining those software engineers. Eventually the software team will have a DBA who will put together a great database for me if I leave the door open to a great database. My job is to make sure the requirements for that database are really, really clear, that whatever they choose to do has to meet my requirements. But other than that, I should stay out of it. That's the challenge when we're doing this. But one of the groups we're going to allocate a lot of our system to is HR. Some of it we allocate to management. Someplace in your technical architecture, you might find you have to update various policies around the company. So I need a new policy on X and a new policy on Y. And those policies will be parts of your technical architecture. And when it comes time to implement them, I allocate policies to my steering committee, my project steering committee, because these are management statements. I'll say, here's 10 policy statements we need updated for this system. When I hand them to the steering committee, says, go write me 10 policy statements that meet these requirements. And they have to be able to do it. But that's why we're thinking of our systems as societal systems. If you think of your system mechanistically, what are the devices and stuff I've got to engineer and build? You're taking a very narrow view. And as system engineers, we want to take that bigger view. It's not just what is the stuff, but how is it going to be used? How is it going to be deployed? How is it going to be maintained? The whole life cycle has to make sense, is really what we're after here.